This problem is specifying the eigenvalues and eigenvectors for a given 3x3 matrix. And if you look at the notes, I have changed the problem. There's now a minus 17 in that row 2, column 3 slot. So to start this problem, as always, we want to look for the eigenvalues of this matrix by looking for the determinant of A minus lambda I. So A minus lambda I involves subtracting lambda off the diagonal entry of the matrix. So 3 minus lambda, 0, 0, 2, 6 minus lambda, minus 17, negative 1, 2, minus 4, minus lambda. And for the determinant, we want to find the right row or column to use. And in this case, we want to use row 1 because it has only one non-zero entry in it. So if we do that, the determinant of A minus lambda I is the following: negative 1 to the 1 plus 1 times 3 minus lambda times the determinant of the corresponding minor, which is 6 minus lambda minus 17, 2 minus 4 minus lambda. We can work out that 2 by 2 directly. It's just AD minus BC, 6 minus lambda minus 4 minus lambda plus 34. Simplifying out the inside, 3 minus lambda. This I have a lambda squared. I see plus 4 minus 6 is minus 2 lambda. Minus 24 plus 34 is plus 10. 3 minus lambda is fine. This last one does not factor. So we'll find our roots by the quadratic formula. So lambda is going to be 2 plus or minus the square root of b squared, which is 4, minus 4ac, which is 40, over 2 is 2 plus or minus square root negative 36 over 2, is 2 plus or minus 6i over 2, or 1 plus or minus 3i. We have our eigenvalues here of 1 plus or minus 3i, and then lambda equals 3 from this term. So let's do the real one first. For lambda equals 3, we subtract 3 off the diagonal, giving us the following matrix: 0, 0, 0, 2, 3, minus 17, negative 1, 2, minus 7. We want to row reduce this, so let's swap the bottom row to the top and divide it by negative 1. Then we can do row 2 minus 2 row 1 to cancel out that 2 in that first spot. That minus 2 of those is minus 1. That minus 2 of those is minus 3. Or 1, 2, minus 7, 0, 1, 3, 0, 0, 0. Right, now as equations, this tells us that v1 plus 2v2 minus 7v3 equals 0, and v2 plus 3v3 equals 0, with v3 being a free variable. In this case, I can choose v3 to be 1. v2 is then negative 3, and plugging those up in my previous equation, v1 will equal 7v3 minus 2v2, or 7 plus 6, or 13. So with that, we get our eigenvector. So for lambda equals 3, the eigenvector that we get is 13 minus 3, 1. Now, for the complex eigenvalue, we're going to choose the 1 plus 3i version. If I pick lambda equals 1 plus 3i, I want to subtract that off the diagonal of the matrix. So 3 minus 1 plus 3i, 0, 0. 2, 6 minus 1 plus 3i, minus 17. Negative 1, 2, negative 4 minus 1 plus 3i. We can simplify this out. This becomes 2 minus 3i, 0, 0. 2, 5 minus 3i, negative 17. Negative 1, 2, negative 5 minus 3i. Now, for this first row operation, I normally don't recommend dividing by complex numbers. However, because the 2 minus 3i is alone in its row, when I divide by 2 minus 3i, I just get 1, 0, 0. So we can just start by doing that. Divide the first row by 2 minus 3i, get to 1, 0, 0, 2, 5 minus 3i, minus 17, negative 1, 2, negative 5 minus 3i. And I can use that 1, 0, 0 to get rid of both the 2 and the minus 1 that are below it. 1, 0, 0, 0, 5 minus 3i, negative 17, 0, 2, minus 5 minus 3i. Great, now I just have this 2 by 2 at the bottom to deal with. And I want to row reduce that to make that make sense. And so I'm going to multiply the second row by the conjugate of that first entry. That's times 5 plus 3i, Multiply that by 5 plus 3i. What I end up with, 1, 0, 0. 0 is down the first column. 5 minus 3i times 5 plus 3i is 25 plus 9, or 34. Negative 17 times 5 plus 3i, 2. Negative 5 minus 3i. If you look at that for long enough, the top row there is just 17 times the bottom one. This will row reduce to 1, 0, 0, 0, 2, minus 5 minus 3i, 0, 0, and 0. So as equations, this tells us that v1 equals 0, 2v2 plus negative 5 minus 3i, v3 equals 0. We know v1 has to be 0. For v2 and v3, we can choose v3 to be 2 and v2 to be 5 plus 3i, because then when I cross multiply those, I get 0. So therefore, for lambda equals 1 plus 3i, my eigenvector that I get is 0, 5 plus 3i, and 2, which also means that for free, I know that for the eigenvalue of 1 minus 3i, I just get the complex conjugate of 0, 5 minus 3i, and 2. This was a case of having one real eigenvalue and two complex eigenvalues, and the process of working out the eigenvectors for those different values. So at the end, we see that for our complex, for 1 plus 3i, we got 0, 5 plus 3i, and 2. For the conjugate of 1 minus 3i, we get the conjugate eigenvector of 0, 5 minus 3i, and 2. And then our real eigenvector was up here. For lambda equals 3, we had an eigenvector of 13, negative 3, and 1.